There is no way you can remember this. This is extremely concentrated. This is very, very fast. Okay, you go. So, I want to tell you about the Euler-Wern-Petersen equations. So, I remind you of my notation. D is the unit disk open. D star is the outside unit disk. L1, L infinity are standard ones with a standard metric. Then, we introduce certain spaces, and D star, which was the null space of a certain projection. I'm going to remind you of it in a second one. In a second, then there is the space omega minus 1, 1 of D star. And here you see this has the norm, the usual measure. This is the measure of the Poincare disk. That's the only thing. Okay. And of course, because you have a direct sum, you have this quotient. Then we discussed quasi-conformal maps, and for you, and for me also, the quasi-conformal map, the quasi-conformal maps are those that solve this equation. d dz bar of phi is equal to mu dz phi, where mu is in L1 log, locally L1. So this is a remarkable PDE, which has solutions as we discussed before. And the universal Teichmüller space is obtained in two ways. There are two models. You solve, one model you go by reflection, and you find solutions. And then you have an equivalence relation that simply says that if on the circle the solutions are the same, the solutions are equivalent. Then you take the unit ball in the outside unit of the unit ball in L1, and you divide by this equivalence. That was the abstract definition, which was terrible, right? Okay, then we tried to understand it, and the bottom line was that there is a Banach manifold structure, complex. In other words, there is the natural projection onto the topological quotient space is in fact a surjective submersion. Therefore, there is a unique complex Banach manifold structure on T1. And to understand what is going on, this space n d star was in fact the kernel of the derivative of the projection. So the tangent space to this manifold is in fact this omega minus 1, 1 d star. So these were the spaces that we introduced. That was one thing. Then we discussed what is quasi-symmetric homeomorphism. Quasi-symmetric homeomorphism is a kind of a multiplicative version of, not quite Lipschitz, sort of Zygmunt kind of conditions, because there is a minus t here and a plus t here. So there are two things. And there were some fundamental theorems here. For example, there's the Boydell-Kalfors extension theorem that says that an orientation preserving homeomorphism of the circle, that means a quasi-conformal extension to the unit disk if and only if it is quasi-symmetric. So what are quasi-symmetric homomorphisms? They are boundary values of quasi-conformal maps. That's how you have to think of them. Okay, so this extension is not unique. This is a source of lots of problems. And the bottom line was, again, that there was a bijection between the universal Teichmüller space, this T1, and quasi-symmetric homomorphisms that fix 3 points. And traditionally, the points are 1, minus 1, and minus I. These are the points that are being fixed. And therefore, the bottom line was that since this is a complex manifold structure, this is a bijection, you move the manifold structure here, so this becomes a complex Banach manifold. On the other hand, this becomes a group, right? And this is the multiplication in the group. And you know, it's a terrible thing because you have to solve the PDE in order to write the multiplication down. But then we have seen several things that the right translation was in fact bihomomorphically, but left translation was not even continuous. So this is worse than the diffeomorphism group. The diffeomorphism groups, remember, for HS or WSP topologies where S is bigger than n over p plus 1, where n is the dimension of the manifold, are topological groups. And the right translation is infinity. Well, this is not, this is worse. So this was the first disease that had to be cured. I mentioned that, be careful, there are two diseases with this space. This is disease number 1, right? But you keep going. Then there is you look at the tangent space at the identity, you want to understand it better. We have the space omega minus 1, 1. In fact, you can show directly that the tangent space to identity is a very well-known space. It's called the Zygmunt space. Yeah, all the U's in C0 S1R. There is a C such that here you see x plus t minus t and minus 2 over u of x is smaller than or equal to c times t. Right? So these are various spaces that are introduced in analysis, in harmonic analysis. Okay, and of course, if I fix 3 points, then of course the tangent vectors here are 0 at those 3 points. Now, the point that I made was that ZS1 contains the vector fields whose flows are quasi-symmetric. This was the theorem of Riemann. I told you there is life below Lipschitz. You can have the right-hand side to be Zygmund space. You still have a flow. Peano does not give you a flow, it gives you existence, but you don't have uniqueness, you have no flow. What we teach our students, and that we know essentially by heart, all of us, is that if the right-hand side is Lipschitz, you have a Lipschitz flow. But you can go below, and you can go below with Zygmund. And this is not very well known. There's a paper in Invenciones by Bernd Riemann in 1976 that he proves that. He does it even for higher dimensions, but we are not interested in this. Now, in 1990, Nagel-Verhofsky introduced what they call a metric. Of course, it's not a metric. Anyway, they give this formula. This formula appears in the Teichmüller spaces, and there is a metric for the finite dimensional ones associated to Fuchsian group or to Riemann surfaces, and they copy the same formula. It looks like a metric, it isn't, because it makes no sense. This formula is divergent. This integral is not convergent, right? So what do we do with it? Well, you look at it more carefully, and in fact you find out that it converges not on all omega minus 1, 1, which is what you need to have, but on a subspace, on an L2 version of that. And here I write it. Are all the mu in omega minus 1, 1, this was sort of like an L1 version, such that mu z squared with the same measure is finite. Okay, so we have this formula which wants to be a metric. We have this index B to remind us that this is a complex Banach manifold, and I'm using the identification that the tangent space at the identity class of 0, the 0 function, is this space, and the derivative of this phi that makes it, that identifies this manifold, in fact sends it to the Zygmund space. So, you want to look now, so this is the Zygmund space, but here, this was inside here. So who is inside Zygmund? Right? So let's see to whom does this space correspond to. Well, it's very easy, well, in principle at least. You take this isomorphism and you take the space that was in here, namely this one, and you push it forward. And look what you get. This is quite amazing. What you get is you can write this formula in Fourier representation in this way. So u and v are the Fourier coefficients, right? You are the circle. You can Fourier extend. This is just complex conjugation, right? And you get n squared minus 1. So you get n to the power 3, right? That means I am in the Sobolev space 3 over 2, right? So suddenly this becomes very, very concrete, right? So this universal Teichmüller space is what? Is quasi-symmetric homeomorphism. I understand what the homeomorphism is, right? Not some crazy class, right? And the tangent space is H3 over 2 periodic functions that I put a 0 there that vanish at 3 points. Minus 1, 1 and minus 1, right? So, unfortunately, 3 over 2 is the critical index. Let's never forget this. Remember, if you want to have diffeomorphisms, you want to solve a differential equation where the right-hand side is of class HS, and you want to have a flow of class HS, you need always n over 2 plus 1, strictly bigger than n over 2 plus 1. Why? Because of the Sobolev theorem. Why? Because you want the C1 maps to be inside there. This is why you need strictly bigger. So I repeat it over and over again. It's n over 2 plus 1 plus epsilon. No matter what epsilon is, but you need that epsilon. Here you don't. You are exactly at 3 over 2. And there are no theorems that tell you that this guy in fact is okay. What do you prove in the Sobolev theory? You prove that if I give you a diffeomorphism of class HS, You use this, the Sobolev embedding, and the inverse function theorem to prove that the inverse is automatically HS. But you need the C1, otherwise you cannot prove it. Here you cannot do it. Okay? So we are faced, in fact, with work at critical Sobolev inverse. So this is hard analysis. This is the warning. But at least I know what I'm talking about. At least I have some objects in my hand that make sense to me. Okay, so where are we? So let's make a summary. We have defined the universal Teichmüller space abstractly, the unit ball in L1 of the outside of the unit disk, divided by this equivalent relation by solving the Beltrami equation. We have the Boiling Alfors bijection that goes from T1 here. We have seen that T1 can be endowed with a Banach manifold structure. Therefore, because of this bijection, this is also a Banach manifold. It is complex, and both of them are in fact quotient manifolds. Okay, no problem. So I can make him into a group, and I can make him. I can give him the metric. The problem is that now I have my second disease. So these are the two diseases. This is not a topological group, and the Weil-Petersson metric is a metric. It's a formula that makes no sense. Right? I cannot have a formula that applies only for some vectors. Right? I have to take two arbitrary tangent vectors and take the inner product. That's what the metric is. I cannot say I'm going to take only some vectors and I can take the inner product. Right? This is unacceptable. So these are the two things. So we have to cure these two diseases. Okay, well, it was not me who did it. It was Leo Taklajan and his postdoc Theo, his student, Theo, from Malaysia. It's a woman I never met. Anyway, so what did they do? Well, the point, it's a very interesting point of view, and many people in Teichmüller theory unfortunately don't like what they did. I don't know why. I personally think this is a fantastic result. But, okay. Well, the fact of the matter is that if you look at the metric, that integral will not converge. No matter what you do, it will not converge. It's not a metric that I cannot prove it convergent. I can prove it's divergent, right? So, I mean, there are examples, right? So what did they say? They said, well, this is the Hilbert space. I need a manifold whose tangent space is this Hilbert space. I have no choice. The only way I can do it is if I have a Hilbert, if I have a manifold whose tangent space is this. On the other hand, so let's see what the problem is. On the other hand, they cannot change the space. This is a big problem. I mean, you see, what do people do in Sobolev space theory? Well, I have HS, where S is bigger than something. I want something more, I have HS plus 1, I have HS plus 2, right? I can always organize it. And then my diffeomorphism becomes smaller. There's more regularity, right? There's no regularity. Here you cannot do it. The object is given to you. That object is quasi-symmetric homeomorphist, whether you like it or not. This is it. Right? You cannot change it. Yet, the manifold structure tells you that you need this. So, this order is very tall. You need to have the same set. Organize it in such a way that the tangent space becomes this. The only thing you know is that you have a continuity from here into here. Yeah, it's like a 2 in a row. Big deal, right? More or less. So here is what they do. It's an absolutely great idea. I'm not going to go into details. Taklajan Theo is almost 200-page paper. It's in memoirs. It's enormous. And I will touch only upon some of the results of Taklajan Theo, the ones that I need. There are many, many, many other results. But it's quite spectacular what they did. You will see in a second. Because I need these results to start doing dynamics. I want to study the geodesics. They didn't, they just did the geometry. So, look, I have a Banach space and I have a subspace. That subspace is not a Banach subspace. because it has its own topology. But the inclusion is continuous. Okay? Now, what do I need to do? I cannot change this space at some level, right? And remember, the set cannot be changed. And this is the tangent space in the complex Banach manifold structure. So this I cannot change. What I can change is only the differentiable structure, not the set. So him I cannot touch. But I want him, but he's smaller. So here is what they do. They say, I will look at this guy as a manifold modeled on this space. See, this, I'm sure you have never seen this idea. So I have a Banach space and I have a subspace with its own vector subspace, with its own structure, and the only thing I have is I have a continuous inclusion. So here's what they say. I need to keep the big space. I have no choice. I must keep it. So, but I want him to be the structure. Well, I can't. I can't win, right? So then they say, well, I'm going to give up the fact that this is a Banach space. I will think of it as a Banach manifold. And the Banach manifold has to be modeled on H minus 1, 1. E is F. It's completely abstract. So here is E, here is F. Now what they do is they take F and put it like this. F plus V, F plus V2, F plus V3. They make a book out of it. Right? Just stack it up with all translations. And they say, these are the connected components of the manifold. There's no problem. Right? They don't talk to each other, they never intersect. My structure is going to be automatically the one that I want, and I have filled the whole space. I pay the price. This big set is not going to be a Banach space anymore. It's a Banach manifold. So this is the idea. So that we understand at linear level. Now you take the charts that the classical people have constructed, right? In the Banach manifold structure, and you play the same game there. Now you've changed the manifold structure, you have not changed the set. Okay, so I'm going to get an H minus 1, 1 Hilbert manifold structure on the same set, the set of equivalence classes, or of quasi-symmetric homeomorphisms. Okay? So I simply restrict the Banach manifold charts from here to there. What's the big deal? Because I know what to do, I just cut them, like this, right? Of course, I'm going to introduce now uncountably many components. Okay, fine, I don't care, alright? Fine, so far so good. You are going to get a Hilbert manifold, which is highly not connected, has uncountably many connected components. Okay, I can live with this. Obviously, I have problems. I mean, certain things have to work. And the amazing thing what these people have shown is that everything works. This is truly amazing. So the sets T1 and this endowed with this Hilbert space topology, I have to denote them differently. So I'm going to put an H here. They are the same sets. I did not change the set. Only the manifold structure has been changed. And now it's going to be a Hilbert manifold structure. Okay. But the bijection is a bijection. Right? So it doesn't matter. So that means that this endows the group, this one, with the structure of a complex Hilbert manifold, because I put it here, therefore it's going to be here. And I know, I just went through this with you 2 slides ago, that if I look at the tangent space, I get H3 over 2 periodic functions that lie at 3 points. Right? So, the connected component of 0, I'm going to denote it with a little circle down there. Right? It's a connected component of the identity in a topological group. And the manifolds T1H and this one, the connected components, have the following very good properties that are proved by Takhtajan and Teo. 1. Right translation is biholomorphic. I didn't lose this property. This one is a topological group. Disease 1 has been cured. I look at this one and I look, which is the same as this one, that's going to be the closure in T1H of the subgroup of C-infinity diffeomorphisms. It's very beautiful. The previous one was not like this. So I take the C-infinity diffeomorphism and I just take the closure in this topology. I get this space. Okay? And now comes a gift from the sky. The Weil-Petersson metric is strong. Not only have I fixed it that it's a metric, it is strong. On T1H, it is the natural Hermitian inner product on the tangent spaces. Now let me emphasize that this is truly something that is somehow too good to be true. You see, in infinite dimensions, the only time I have seen something that has strong metrics in my entire life were things related to quantum mechanics. Right? Because what do you do there? You take the imaginary part up to constants and minuses and h bars, whatever, of the Hermitian inner product. And then when you go to projective spaces or to Grassmann manifolds, these are all quotients of this type. So the metrics remain strong. These are the only ones I have seen. Whenever you do PDEs, they are never strong. For example, the Arnold thing that he has done, you know, it's L2 metric on HS vector fields. Cannot be strong. The topologies are vastly different, right? Okay, here it's strong. So this is going to give me great results. Okay, here is what I prove more. I mean, to get to this result, you must have read about 100 pages of the paper. You look at the identity component, and then there is a J. Who's this J? Multiplied by I. Literally, multiplied by I. And omega is a strong Kähler-Einstein-Hilbert manifold with negative constant Ricci curvature and negative sectional and holomorphic sectional curvatures. This is fantastic. Now let me make some remarks. For S bigger than 3/2, this group here has exactly the same properties. So let's see what the parallelism is. It is a smooth Hilbert manifold, a topological group, smooth right translation, modeled on the Hilbert space HS. Right? But it's strictly bigger than 3/2. You cannot put 3/2. It contains the Freshelli group of C-infinity diffeomorphisms on the circle as a dense subgroup, exactly as we have seen before. Therefore, who is the Lie group whose, whatever, in some sense, in this vague sense, whose Lie algebra are H3/2 vector fields, not diffeomorphisms of class 3/2, the quasi-symmetrical homomorphisms. It's a new object. So this is the one that replaces this if at critical Sobolev index. Okay, and indeed, yeah, well, here it is. Now, here is an open problem. It's difficult. I'm telling you, I try to do it, I can't do it. I talked to Leon Tachlerjan also. We don't know how to do it. We have no intrinsic description of this group. I cannot tell you who it is. You know, to put my hands on it. How many derivatives do I have to take? What do I have to check? What is the condition? Right? We only know that it is the completion of this in here relative to this Tekla-Janteo topology, which I understand. But this is not explicit, since it is defined through the map phi. Remember, phi was a bijection that was given by solving the Beltrami PD, and God help you, right? How are we going to do this concretely? How are we going to describe these objects? I don't know. Now, is there a regularity? Can you say anything about it? Yes, you can. At least I can tell you something. This connected component of the identity in the Hilbert topology sits in what I call diffeomorphisms of 3/2 minus of S1. Who are those? These are all the orientation preserving homeomorphisms of S1 such that both eta and eta minus 1 are in here. You see, remember, if this was a plus, if I tell you that eta is in there, the inverse function theorem plus Sobolev embedding guarantees that eta minus 1 sits in there. If I'm a critical or below, this is worse, this is below critical index, I cannot do this. I have to put both conditions. Okay? So I put them both. So I'm telling you that this object here are all the homeomorphisms such that them and their inverses sits in H3 over 2 minus epsilon for any possible epsilon. And in fact, this object itself is a topological group. This is hard to prove. This is not easy to prove. This is one of the things that we did with Francois. Okay, I will probably not tell you how to do. Well, in order to prove this result, what do you need? You need to multiply, because you want to use the chain rule, and compose below critical index. Literally, below critical index. So we have to prove some very hard analysis theorems that show that this is possible. Okay, so for you at this point, the only thing I wanted to point out, that this exists, this is a topological group, and all of them are in here. This is difficult. This is genuinely difficult. Okay. So, let's go now and do geodesics, right? So I told you what Taklajan Teo did, and I told you what we have added to the geometry. They never work with quasi-symmetrics, Taklajan Teo. They don't need them. They just want to understand the geometry. They work with this very abstract space, T1. Okay? Now, what do we know? Let me make a list of things that we know. Eta T is a geodesic in the diffeomorphism group of class HS that preserves the volume for mu, where mu is the Riemannian volume of the Riemannian manifold N, for the L2 metric if and only if the Eulerian velocity, which is given as eta dot t composite eta t minus 1, is solution of the Euler equation. This is Arnauld plus Ebermaster. Arnauld did it formally. He simply took C infinity and he said, I don't care what it is. Ebermaster took it seriously. This is not a Lie group, because the left translation and inversion are not smooth. They proved for the first time that on a general manifold in any dimension that the Euler equations have existence, uniqueness, and continuous dependence on initial conditions. How did they prove it? They proved it by showing that in the material representation, if you look at the tangent bundle of the diffeomorphism group, you have a geodesic spread. So you take the L2 metric, and the L2 metric is naturally right invariant on the group. Arnauld showed us how to do this. Then they showed this is their paper. I mean, everything else is consequence of this. 99% of the paper is this result. That the geodesic spread is smooth. This is hard to show. This is all they show. The rest, and then they can conclude many results. For example, once you know this fact, there's no problem. You have a Banach manifold, and you have a smooth vector field. What is the problem? Of course, you have existence and uniqueness, right? So you have existence and uniqueness, which is eta t. Therefore, obviously, you have eta dot t, eta t minus 1. What is the problem? Okay? But you know that if it's smooth, the dependence on the initial condition is also smooth by the theorem that we teach our students, right? Look what's happening here. I'm multiplying on the right, this is wonderful, but not with eta inverse. And taking the inverse is only continuous, it's not C infinity. Therefore, all the derivatives have gone. All that is left is continuous dependence on initial conditions. You cannot do better by this formula. So they proved what the PD people want to do. Continuous dependence on initial conditions. But in fact, they proved more. They show that in material representation, the dependence is infinity. This result is being discovered every 4 or 5 years by some famous guy. because they don't know geometry, they can't read the paper, and they want to do their estimates, then they work very hard and get this, what a great result. And then they discover it as well. Okay, there is another equation for which the same method works. This is called the n-dimensional Kamasa-Holm equation. So, Holm you will meet, is a very good friend of mine, I'll bring him here, and also Roberto Kamasa. So, these people, it's a very interesting story how they did it. You know, there are various things that are very high fashion. It has to be bio-nano or climate change, right? Everybody is saying this word gets money, right? So, these people took it seriously and were interested in ocean models. I mean, Holm especially, who's a physicist at the origin, he's now in the math department, he's a physicist, was interested in trying to understand ocean dynamics. Because the ocean, completely, but has a huge influence on the climate of the Earth, right? And of course, the answer is, well, study Navier-Stokes models, thank you very much. Let's be serious. So then there are various approximate models that meteorologists have introduced. Very interesting approximate models. So at a certain point, they started playing with this. I remember being with Holm in a meeting, and he put a slide up like this, and he had in every little corner like this, a little equation. Many equations, you know, all the approximate models. And eventually, he came down to a one-dimensional ocean. Okay, it's kind of a joke, right? And this is the famous Kamasa-Holm equation in one dimension. Now, the Kamasa-Holm equation has a generalization, of course, in n dimensions. And this equation is not an equation that is purely PD. It's an integral differential equation. An equation with a pseudo-differential operator. So let me show it to you. So there is, I forgot to write the u here, or dt applies to u. So this is dtu plus nabla um plus nabla u transpose. You think of nabla u as a 1-1 tensor and transpose relative to the metric. So you flip both indices with a gij, right? You apply m to it, I tell you when m who it is in a second, plus m divergence of v is equal to 0. Where m is this object, is the Ricci Laplacian. It's a regularization operator, 1 minus alpha square Laplacian, Hodge Laplacian, d delta plus delta d, plus Ricci curvature. On u. Okay. So obviously, if I plug this in, if I want a revolutionary equation on u, I will have to invert this, right? So it's quite an ugly object. Okay? So the same method that worked here works here. This was part of the thesis, one chapter in the thesis of François Guérin, who was my student. So this is a beautiful result. The same type of result works. It's much tougher, but it works. Okay, so let's come to our problem. So eta t is a geodesic here for the Wald-Petersson metric, if and only if I want to say this is a solution of the Euler-Wald-Petersson equation. Who is this equation? Okay? Can I tell you who this equation is? Can I give you existence uniqueness? What do I know about this equation? So, there is a fundamental difference. In the first two problems, the metric is weak. You have enormous problems in analysis because the matrix is weak. For example, how do you prove that you have a connection? Well, we know how to prove you have a Levi-Civita connection. We write the condition nabla g equal to 0, we apply nabla g to xy, we get a horrendous expression, right? And then we get g of nabla xy comma z equal to, right? And then we say, well, it's finished because I just told you the inner product of nabla xy with anybody, right? In finite dimension, this is perfect. In infinite dimension, it's not. If the metric is weak, this proves uniqueness. Does not prove existence, right? Because I cannot solve it, right? I have only injectivity, I don't have surjectivity, and I'm guaranteed not to have it. It's not that I cannot fix it, I'm guaranteed not to have it. So you have to do something else, and in fact, this is part of the work that I François Guérin I told you previously. In fact, there is a Levi-Città connection for these matrix, and of course the proof does not go like this. You have to work with a connector and so on. But okay, these are technicalities. So, but the topology is standard, it's going to be Sobolev. The difficulty is to prove the existence of the smooth geodesic spray associated with the Dicke metric. That is what is difficult. A priori, you cannot do this, right? A priori, you will have, it's like an unbounded operator, yeah? A priori, you are going to have some vector field that is defined only on some open dense sets of manifold. But, so sorry, that's not a vector field, right? Because I can't take, it's not a section. There are points where I'm not allowed to take, right? For 3, these problems are completely gone. It's like in finite dimension, the metric is round. Therefore, the geodesic spray is smooth. But now I have a problem. So I can write abstractly eta double dot is equal to some smooth vector field eta dot. The question here is, what are the PDEs going with it? Which I don't know. Okay. In addition, we can prove that the solution exists for all time. So we have a long time existence. This is wonderful. So the difficulty here is related to the fact that the topology is not explicit. Remember, it's induced by the Beltrami equation. Can't really work with it. How can we pass from the ODE in infinite dimensions for eta to a PDE in finite dimensions for the Eulerian velocity? This is the question. And that again uses multiplication and composition below critical index. So the same difficulty that appeared before, just as a question, appears again here. So you use the same type of analysis that you do once. So let me tell you what is known. Let eta t be a geodesic of the Weil-Petersen metric on this. Then I have this curve, which has values in h3 over 2, is continuous, is C1 with values in h1 over 2, and is defined on the whole of R. So the way like the PDE people like to write, you have a map like this. It's C0 with values in h3 over 2, and C1 with values in h1 over 2. Right? The derivative is given by, you see the transport here, I mean one dimension, so there is no nabla is prime. So dtu plus ux, x being on the circle, u prime u, plus something equal to 0. And that something is a continuous map from h3 over 2 to h3 over 2, which in principle can be written down. It's not very explicit, but there is a PDE that goes with it. This is the geometric form of Euler-Weil-Petersen, and Z is not as explicit as you may like it. Okay, now, assume that you want to apply blindly Euler-Poincare formulas, as I did formally for liquid crystals. After all, it's geodesics, why not? You run into trouble, it will not work. The topology, the manifold structure is very, 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 very tight. You are going to run into operations that are illegal. So you cannot have such things. So let me show you why not. For example, I take the L2 pairing and I'm going to write the Lagrangian as some operator on U with U. And this operator, in fact, I can write down. It's going from HS to HS minus 3, right? So it's going to be an unbounded operator, right? Here it's continuous, but on HS minus 3 is unbounded. It's a symmetric operator, which is given in this fashion. Okay, I just write it. Here are the 3 points. If it fixes 3 points, it misses 3 coefficients. Exactly the coefficients where these guys are 0. Plus, minus 1, and 0. Okay? Now, I can sit down and compute. I have formulas, remember? Euler-Poincare. So I can write the equation down. Here it is. M dot plus 2mu prime plus m prime u equal to 0. Where m is q op of u. Where q op is given this. So it's all explicit. This equation makes no sense if u is in h3 over 2. Remember, I'm stuck with h3 over 2. I cannot change the differentiability degree. Right? But there are classes of special solutions nevertheless. For example, you can write it in, you want to write it in weak form. Right? M prime phi plus M u prime phi is minus this is equal to 0 for any phi to be C infinity on the circle. This makes sense. And then you get what is called the tachons. You get like solitons. This equation has soliton-like solutions. And here they are, they're given by some function pj, and then here some function, some Green function in fact, and this Green's function is given here. It's explicitly written down. It's the Green's function that goes with the operator Q. Okay, here is a second order problem. Here is a conjecture. I don't know how to prove it. Given U0 here, we know from Riemann that there exists a unique flow for this equation. Okay? Such that this is quasi-symmetric for all t. Right? The Zygmunt writes, here it's H3 over 2, it's going to be Zygmunt, that I already showed you. So therefore, being Zygmunt is quasi-symmetric. It has to be more than quasi-symmetric, right? But we need more. We need to prove that the curve from t to eta of t lies in here and is differentiable with respect to the Hilbert manifold structure of this. I'm telling you that I want this to be the exponential map if this would be a Lie group, right? But you have to prove it. It's not a Lie group, right? Everything has to be done by hand. How did I do it how do you do it for diffeomorphism groups? Well, very simple. It's the flow theorem. The exponential map is, if I take x, the vector field, what is the exponential map of x for the diffeomorphism group? It's the flow of x. And now you quote theorems about the flow. I cannot quote theorems about the flow, because I have none. Nobody's proved it. So, however, if this is true, you immediately have three theorems. And they're fantastic. That means that this guy contains exactly the flows of time-dependent vector field with values in H3 over 2. No more and no less. So far I only showed that they are in here. But I didn't show you that there may be others that are... how do I know that I get everybody? I don't. Then I would know. That's it. No more. Okay. So I recall for you that this contains exactly the flows of time-dependent vector field, what I said a moment ago. When S is 3 over 2. You see? If S would be strictly bigger than 3 over 2, this result would be true. It's known. For any manifold. Forget the circle. It says that contains exactly the flows of the time-dependent vector fields U continuously valued in HS for S strictly bigger than 3 over 2. I would like to show the same thing for S equal to 3 over 2. I don't know how to do it. But I would, but this would be a corollary of this theorem. Another corollary of this theorem would be there exists an eta here which is not in 3 over 2, H3 over 2. Right? And the third corollary would mean that for all S strictly bigger than 3 over 2, we have this inside here. This I never proved. I could only see infinity. I could not show for work. They are extremely natural. It's hard for me to believe that these things are not true. I mean, this is so natural that it has to be true. But I don't know how to prove this. They really tried. I don't know how to. So this is a big open problem. This is analysis, and it's hard analysis. So, this is the problem. Now, there are applications of this which I haven't gone to. For example, there was a thesis of a student, it was a Russian student, I forgot his name, of David Mumford, who has worked very hard to show that tachons exist for all time. Right? We can do this like this. There is no problem. Because his tachons, in fact, are exactly the Euler-Poincaré equations that I showed. He puts more differentiability conditions than we need, and therefore these equations make sense. And if they make sense, these are the equations. And we have already proved long time existence. I mean, it's, you know, the proof is a matter of half a page. The more interesting thing is again a problem that came from Mumford. There is the problem of image registration. So let me start sort of with a joke what these people want to. Imagine, I mean, we are not far away from these times. This is going to happen within a few years. You know, you're not going to go to the AMT machine and get cash out anymore with your card. The AMT machine will look at you and will know it's you, right? But there is a problem. The problem is that you made a picture, right, 5 years ago, you were nicely dressed, make a picture, and now 5 years later, you come after a party at 3 in the morning and you're trying to pull money out. You look awful. How does the machine know it's you? Right? So it has to compare. So what did Mumford, this is a fundamental idea of Mumford in computer vision and in image registration. He says, I will compare these pictures. Right? To compare these pictures means I need a metric. Right? Metric means geodesic. So if this is very short, it's you. If it's long, it's not you. Right? It's very, very simple. Right? In principle. And what does he do? He started using, of course, Arnold diffeomorphism groups, right? Because these are just curves, right? Or in the embedding version thereof. And they use L2. This is a problem in L2. Because he himself proved, in a paper with Michor, he proved that the distance function for the L2 metric could be 0 with 2 different diffeomorphisms. So it's not a metric, it's a semi-metric. That's bad, because that means that 2 different people could be the same person, right? The machine would give money to somebody else, right? This is no good. So then they looked for other metrics. They came to this one, to the Weil-Petersen metric. So in one of their papers, they needed to know that it's quite a complicated thing. You take a sphere, you have a diffeomorphism on the sphere because of this, and you have to glue them like a diffeomorphism. You have what is called the fingerprint. There's a whole edifice that goes with it. At a certain point, there is a technical point. He needs to know that this image can be connected with this image by a geodesic in the Weil-Petersen metric. Yes, it can be. Our theorems can show this is correct. Not trivial, but not too complicated. Okay. So I presented something quite pure. Now let me present to you something more applied. Okay? We alternate it like this. So this is what we call Krebs optimal control problem. There may be, we may have not done it rightly because apparently there is something already taken like this. Anyway, let me show you something that that you know. Okay? This is symmetric rigid body in n dimension. Okay? You don't know what symmetric is. You know what rigid body is. It's the Markov system. M not equal to m bracket omega, where m is omega j plus j omega. Right? I preach here to the converter. You all know this. Otherwise you wouldn't be in this room. Right? This is the first generalization of the rigid body. Right? Now I'm going to show you something very strange. I'm going to give you a so-called symmetric representation, and I'm going to show you this is an optimal control. Okay. So, here is what I do. At this point, don't ask me why. I will tell you what the control problem is in a second. I take a time, and I take 2 points in the group SOM. So, I will baptize this problem, the rigid body optimal control problem, to do the following thing. Well, there is a 1/4 here. This is coming because x dot y is 1 minus 1/2 of trace of the product of the matrices. Right? And I have here u in little SOM, skew-symmetric matrix. I have here an operator. I'm going to call it j of u. Right? This is the moment of inertia operator. Right? And I want to minimize this cost subject to a constraint, subject to a certain physical law. The physical law is the following. I want to solve the time-dependent equation, the linear equation with time-dependent coefficient, quadratures. Q naught is equal to QU, but such that I start here and end up here. Okay? So let me tell you what is true. So, this rigid body optimal control problem has an optimal evolution, has its optimal evolution equation, a certain equation that I'll show you in a moment, where P is the constant vector given by the Pontryagin maximum principle. And the optimal control in this case is given by U equal to J minus 1 QTP minus PTQ. And the way you do it, you don't ask, I'm not allowed to speak like this because I haven't told you anything, and in fact it's not completely clean what I'm doing. I'm going to apply Pontryagin maximum principle like an engineer. Well, it's not exactly what Pontryagin says, but let me apply it, and it works. Okay, this is what Pontryagin does. Okay, you will see all these things in great detail. So, I want you to tell you that there are no constraints. Here, you can change the matrices, etc., etc. The one point that's important is that you can discretize this. You can do numerical analysis out of this. So the question is, what does this all mean? So let me step back and let me tell you what optimal control is. Okay? I'm going to give you a smooth version thereof, which I wouldn't dare to talk to an engineer like this, because they never have smooth versions. So they have a lot of analysis, a huge amount of analysis that you need for optimal control. I shove under the rug because I see infinity, so it doesn't exist. Right? So I give you a Q manifold. I give you U a vector space. Then you ask, why not manifold? Damn good question! Nobody's done it. It's not easy. In fact, there is a thesis in Spain that came out last year that of somebody who is managing to replace this by a vector bundle. But somebody has to go through this very carefully. Right? But this is the state of the art. G is a map from Q cross U into R. This map, this function I will call cost. Then I have some physical law. That means that I have a vector field. So actually it's a vector field that depends on a parameter. That means that, you know, for every U frozen, I have a vector field. But this map is smooth. Right? Everything is okay. So then I give you, so I give you a Q, I give you a U, I give you a G, I give you a physical law or some differential equation, right, that's X, and I give you 2 points, Q0, Qt, and Q, and I want to solve the following optimal control. The optimal control problem in its ultimate abstraction goes like this. Find 2 curves, Q of t and U of t. Q of t solution, U of t some curve in the space of parameters that minimize the total cost, which is the integral Q of t, U of t, subject to the following conditions. You must obey the physical law, Q dot is equal to X of Q of t, U of t, and you want to go from Q0 and reach Qt. Right? Why is so much money involved in this? Very simple. I have so much gasoline, I have a fighter jet plane, I literally mean it, which has to obey the laws of hydrodynamics. I want to leave here and bomb here with a minimal amount of fuel. Right? This is where the money comes from. In all countries in the world, for such problems. Literally. Right? Now, Pontryagin comes along, and this is the best known result today since Pontryagin. It's quite astounding. It hasn't been improved. All the improvements have been technical on the sides, nothing conceptual. So Pontryagin says, watch what he's doing, it's absolutely amazing. He says, I will pick out of my pocket something that looks like a Legendre transform. So what do? I'm going to construct for you a Hamiltonian on T star Q, depending on a parameter U. Okay? There was no Hamiltonian here, please. Had nothing to do with Hamiltonian, right? This is the general problem. Okay? He introduces a Hamiltonian by looking at the cotangent bundle. Okay? And this one is exactly as this is, right? P, Q dot, minus the Lagrangian. Well, there is no Lagrangian. Ah, what the heck. I make U to be the Lagrangian. Even though he doesn't depend on velocities. What the heck, I can do this. Right? This is what he's doing. And he puts some Lagrange multiplier in front. I'm going to come back on this. As GQ of U, where P0 is bigger than or equal to 0, is a fixed positive constant. Okay? So he says, do this. Then he proves what is the holy Pontryagin maximum principle, right? He says the following thing. Watch this. This is fantastic. If Q of t, U of t is a solution of this optimal control problem, then there is a solution alpha t in the phase space, state system of Q, of this Hamiltonian system that depends on a parameter U, right? Here it is, Hamilton's equations, where this H hat, in fact, is obtained in the following way. See, here it depends on U. Now you don't depend on U. You compute the maximum, that's why the max is called the maximum, of all H hat alpha t of U over all the possible U's. Okay? And this is the Hamiltonian vector field defined by if you freeze U. Right? He gives you a sufficient condition. In other words, you want the solution of that, you better solve this guy. That's what he's telling you. That's what Poincare is telling you. And I know of no one who ultimately does not have to do this in control theory. This is the theorem in control theory. Now let me show you how concrete this is. If P0 is different from 0, obviously if I replace alpha t by alpha t over P0, shows that in H hat, one can always assume that P0 is 1. So I really have P0 is 1 or P0 is 0. Right? That much. Solutions with P0 equal to 0 are called normal extremas. Solutions with P0 equal to 0, look here what this means. This means that somehow in the Legendre transform I kill the Lagrange, which I can never, ever possibly do, right, in mechanics. Right? But here it happens. These are called abnormal extremas. And there's been a lot of work on abnormal extremas ever since way back when, since Pontryagin. Okay. From now on, I will simplify my life only with normal extremas when P0 is 1. Let's see what happens if this object here, so you can clearly see that I have problems with differentiability. How do I know this is okay? I don't. Right? So people in control, they have to come to terms with this. Because in control, there is what is called the bang-bang theory, right? I mean, you have something that hits the walls, right? So this is as bad as you can get, right? Okay, but if this happens to be H1, then the optimal control U of t, how do you find it? Well, you have a max. We know from high school what to do. You kill the derivative, right? You kill the derivative and solve. So I need the inverse function theorem, right? So a sufficient condition that guarantees that the maximum will achieve along the control U of t is that x is linear, in fact, it turns out, and that g is strictly convex. That's where it's coming from. Now we can apply the inverse function theorem. In this case, the optimal control is uniquely determined, and I am not losing derivatives. This is wishful thinking in practice for engineers. But look, just to understand how powerful this is, I'm solving my problem. So, locally, the Pontryagin maximum principle states what? It states that alpha t, which is Q of t, P of t, were local, and U of t are determined by the following systems of equations. This is 0, Q dot is this, but this is this. Right? Because it's PQ dot, right? And P dot is equal to this. These are Hamilton's equations, but they're in fact simple. See, there is no P dependence here. This is wonderful. If the DH can be solved, then I solve it, forget him, plug him here, you have Hamilton's equation. This is a Pontryagin. It's extremely beautiful. It's a genius, right? This happens locally, for example, if H hat is of class C2, the second variation computed to the given point is an isomorphism, and if X is linear and G is strictly convex, then these things are guaranteed. Linear controls are common, fortunately. Where you get to go wrong is here. Okay. Of course, once you have this, these equations can be obtained because they're Hamilton's equation by Hamilton's variational principle. And we have already seen, when I discussed it with crystals, that each time I have such a thing, I have numerical algorithms. This is very good. Okay, now let me introduce what I call the Clebsch optimal control problems. It's going to be a control problem. The only thing I give you, in addition to a standard one, and it makes a big difference, is I give you a group action. Left or right group action. On a manifold. Here is my infinitesimal generator. I remind you the definition, as usual. So the Clebsch optimal control problem is the following. I give you a cost, which I'm going to call little l. My linear space is going to be the Lie algebra, G. Find U of t, Q of t, such that you minimize this Lagrangian on G. L is the cost function, subject to the following conditions. You want to get from Q0 to Qt, and you want to obey some law. What is the most stupid law you can imagine? Infinitesimal generator. So, I take U of t, I take its infinitesimal generator, right? That's a vector field. I'm allowed to apply it at any point, and I'm going to apply it to Q of the same t. Right? It's a strange problem, but there it is. Right? Or if you want, one is left and one is right, the other one is going with a minus. I mean, this is not important. Okay, and then we call the inverse representation or something. Okay, so again I repeat, here U is equal to G, my cost, look, it doesn't even depend on Q. I simplify the problem, and my vector field is this, which is linear. Right? So this should be a good problem, because half of those sufficient conditions require that the vector field be linear. This is automatically linear. Okay? It's infinitesimal generator. Okay, what is the Pontryagin function? So let's go by the book, okay? So I compute h hat of alpha q. Well, I know what it is, forget the plus minuses. It's alpha q on x, here is my x, minus the cost. Look at this formula, alpha q on infinitesimal generator on q. This is the formula you know. It is the momentum map of the lifted action. So I'm going to have serious symplectic geometry. That's the first thing. Okay. And this is, J is literally the momentum map. You know what I'm saying. You have G acting on Q, you lift it to T star Q, and this is a momentum map. It's equivalent. What is the formula for this momentum map? Well, it's this one, literally this one, theorem. Right? So, here is a theorem. Let's go through this theorem. Just a statement. Assume that the map from U into del L del U is a diffeomorphism. In other words, I would like to have that the Legendre transform is a diffeomorphism. This is the reduced Legendre transform. Let G act on the left, forget right. Then an extremal solution of the Clebsch optimal control problem, the first condition, is a solution of the L del U is J of alpha, alpha dot is the infinitesimal generator of the lifted action at alpha. Moreover, the solution I can write down, it is the action of G of t lifted to the cotangent bundle applied to the initial condition, where U is the Eulerian velocity here, because I put GT on the right, otherwise it would be the convective velocity here. In addition to that, this equation implied Euler-Poincaré equations. There was no reason to have Euler-Poincaré. Come from the sky. For the control U. Let's go through the theorem backwards. I want to solve my problem. What do I have to solve? Find the U and find the Q. Alright? How do I find the U? Solve Euler-Poincaré. This is a gift from heaven. No Q, no nothing. Imagine this would be, this is Hamilton's equations, right? It's a Poisson equation, if I go to the Hamiltonian. If this is completely integrable, I'm finished. Okay? So, if it's not, I do it numerically, because it's a variational problem. Remember, this equation comes with a variational principle, with the Euler-Poincaré variational principle. Therefore, there are algorithms that go with it. Okay? So, look, I solved the problem. Solve this equation, either if it's integrable or numerically. Now you know u. But if you know u, you solve a linear equation with time-dependent coefficients. Now you got g, right? But if you have g, you have alpha t, because all you do is you act on it. But if you have alpha t, you certainly have this foot point, which is q of t, over. I solved the problem. It's quite amazing. It's a complete solution of the problem. Okay, and let me not go through the proof. It's late. You had too many things. Forget the inverse representation. There is another symplectic comment here that is interesting. Let me compute the h hat that comes from Pontryagin. Again, be careful. And then I can write it down, and it turns out that it is a function of J alpha. It is what is called collective Hamiltonian. Right? The Hamiltonian on T star Q comes by pulling back a function, the Hamiltonian on G star, by the momentum. Okay, I'll tell you much more about this. This, of course, requires this to be a diffeomorphism. Okay, let's do an example. Let's do the simplest possible example that I can think of. L is the kinetic energy of an inner product on the vector space U. The vector space U is G. So let's assume, for example, that my Lie algebra is compact, right? I take minus the Killing form, I have a metric, right? And therefore I have a norm, and I take Lu to be this. What do I get? Right? Well, I know what I get. All I have to go back to the theorem, right? But what I want to do is I'm interested in this guy, because I know that my function of alpha has to be a function of, it depends on alpha only through J of alpha. That's what I showed here. And there is no question that this is not invertible. Right? It's a metric. So, what do I get? H of alpha is 1/2 norm square of J of alpha. I don't know how many of you have worked on the convexity properties of the momentum map here. In the convexity properties of the momentum map, the function with which you work is this one. You do Morse theory for this, to prove that the image of the momentum map is a convex compact polygon. So the ultimate theorem is Kerman theorem that comes from Atiyah and from Sternberg and Kerman, and etc., etc. It has been various versions. It simply says that if you have a compact connected manifold, you have an equivalent momentum map of a compact group, then you have J going from this symplectic manifold to G star. You look at the image, you intersect with the positive algebra. This is a compact convex polygon. And this is at the root of Hamiltonian bifurcation theory, which I mentioned last time. Again, I come back over and over to this. This object keeps showing up. It's screaming, I am here, do something with me. Right? What does this mean? I mean, I am doing a control problem. I'm an engineer. I am not a symplectic geometer now. And look. Why? I have no idea. Are the convexity theorems really controlled theory theorems? I have no idea. If they are, what are those theorems? Somebody being convex is extremely important. There are people spending their lifetime on convex analysis, right? Subgradients and differential inclusions and all of this. I mean, there are people all their life, that's all they're doing, right? I don't know, but this cannot be an accident. Or is there a control theory proof of this? And if there is a control theory proof, what other theorems can we prove in symplectic geometry that are like this? I have no idea. Okay? Here are questions that are fantastic. The restriction to geometry, geodesics, and the normal method. Let me tell you a story here. If I give you my Lie loop is compact, let's make life as easy as possible. Okay? Compactly. I look at adjoint orbits which are the same as coadjoint orbits. We have a symplectic form that is given by Kirchhoff-Kosten-Versuch. We know it. Question. Are there metrics on the orbit that are also not given? The answer is yes, except they come by the truckload. There are many metrics. Okay? So let me talk to you a few metrics. For example, what is the most stupid metric you can think of? Well, here is the orbit. It sits in G. G is a linear space with a linear product. Well, so it's a Riemannian manifold in a rather idiotic manner, right? Pull back. Right? We do this all the time. We look at the Euclidean inner product in R3 and pull back to a metric on the sphere. It's not a stupid metric, as we know. Right? This is something that is interesting. Is this the only way to do it? Oh no, there is another one. Here is my inner product, right? And here is my orbit. My orbit is the group divided by the isotropic subgroup of a point. Right? But if I have an inner product on the Lie algebra, I can make this inner product left invariant Riemannian metric on the group. Right? Now my group becomes a Riemannian manifold. I divide by the isotropic group. The metric drops to the quotient. Right? What is the distance function? It's the distance between two orbits, the metric distance, right? Okay. So this is a Riemannian manifold. But this is in bijective correspondence with the orbit. Right? So take this metric and put it there. What is it? Not the one I told you before. Guaranteed no. It's another metric. Now there are other ones. These metrics in general are not Kähler. Right? But there is a classification of Kähler metrics given by Borel and Weil, who tell us that all the Kähler metrics that are G-invariant are classified by the positive Weil chamber. Right? Now let's understand what this is saying. It says, remember, if I have an orbit and I cut the Lie algebra, right? The orbit that cuts the Lie algebra is going to be a discrete set of points. The discrete set of points is going to be the orbit of the Weil group. There is only one point in each chamber. For example, let's take the positive algebra. There's only one point, positive relative to a certain, everything is very simple. Put anything you want, right? Some order in it, show some order and it's finished, right? I pick this up. So, what Borel and Weil tell you is that for every point in the positive Weil chamber, you're going to find a Kähler metric that is G-invariant. For example, you're going to find the Kähler metric that goes with that point. But you can ask other questions. When is it Kähler-Einstein? I just talked about Kähler-Einstein a moment ago, when I did with Van Petersen, right? Question, I have this orbit. To what point in the positive Weil chamber corresponds that this is Kähler-Einstein? Completely natural question. There is a book written about this. It's Besse's second book. It's called Einstein Manifolds. There's a whole book. Besse is not a person, it's like Bourbaki. Arthur Besse is not a person, it's the seminar of Bourguignon. Right? It's not one person. So, but this is all having to do with groups, right? Now I'm going to show you that the normal metric generalizes Weil metric. And it comes in naturally because of the, and I'll tell you what the formula for it is, and I'm going to show you what it does. So, there are three simple observations. The canonical Hamilton equations, which is this one, we have seen that these equations are in fact Hamilton's equations. In fact, we know that, because this object here has to be coming from the momentum map. Right? Because that's why I have a momentum map. Induce canonical equation on T star O, where O is any orbit that you want to pick up. So I have an orbit I take Q, and then I take the orbit. The theorems work for any G manifold Q. So in particular it works, the Krebs-Optimal control problem can be put on O. Why not? Right? So, in particular, the solution to Euler-Poincaré equations for L are obtained by solving canonical Hamilton's equation on the orbit. Well, of course this was expected, I'm not telling you anything new. Right? I'm just restating things in a different way. Since the solution is given by the action, and thus preserves the orbits. Now, this we know that this is associated to the canonical symplectic form, let's call it omega O on T star of O, and to the momentum function called P of U, which is given by the formula I just gave you before, called the J. So now I want to distinguish P of U. Now, let's assume that L is the kinetic energy of a positive definite inner product gamma on G. Right? You can do this if G is compact. Given Q in Q, let G index Q be the isotropy algebra, the symmetry algebra. All the infinitesimal generators die. Their flows, which are given by the exponential map, keep Q fixed. Orthogonally decompose, I can because I have a metric, an inner product. C in a C cubed with lower Q that sits here, and then upper Q that sits in the orthogonal complement. Right? Define, I'm going to tell you define, but in fact it's not like this is what I told you before. The normal Riemannian metric gamma O on the G orbit with the following formula. Watch this formula, it's very interesting. I am on the orbit. I have to compute at the point Q, right? Therefore I have to take two tangent vectors to the orbit. But any tangent vector to the orbit is given by the infinitesimal generators. So, it's given in this way, XO, infinitesimal generator on the orbit of Q, which is the same as the infinitesimal generator for the manifold at Q, because it's necessarily tangent to the orbit. And I do the same thing with eta. I have to give you a number. Who's that number? That number is the inner product of the following two vectors. Look at Xi, look at eta. Decompose Xi in this fashion, and decompose eta in the same fashion, and pick up the second component. Then take their inner product. There are many things you have to prove here. You have to prove it's well defined. That's not too difficult. You have to prove it's smooth. That's another story. That is not a walk in the park, I guarantee you that. Because you are starting to move the Qs. It's not very difficult, but it's not something odd, of course. No. You have to prove something. So, this formula in fact recovers if the orbit would be a adjoint orbit, and if my manifold Q would have been the algebra with an invariant inner product, recovers the story I gave you before. Highly non-trivial statement, but it's true. Okay. Now, I have to tell you something on locally free, I forget that. That's not so important. Let's go back. So I take my H that is associated to my Lagrangian. So here is a theorem. Denoting by Sharp the usual index raising operator associated to gamma and gamma O, we have that the Hamiltonian vector field is just the kinetic energy on forms. G upper ij, P lower I, P lower J. If the inner product is invariant, then the normal metric is in fact also G invariant. So, what have I done? If G acts on the left, on gamma, and gamma is positive definite inner product on G, and I take a Lagrangian to be just a kinetic energy, then an extremal solution of the Clebsch optimal control problem is given by simply take, and the alpha t, I'll tell you what this is in a second, compute the J and make it into a vector relative to the dot product that I gave you before. Right? Where alpha t star projects to a geodesic on a G orbit in Q for the normal Riemannian metric that I gave you before, gamma O. Here it's again the definition. Moreover, this curve is given by, exactly as I know, I simply act by G of t, and I know how to solve the problem. Right? So I can do this. So, Euler-Poincaré theory guarantees to you that G of t is a geodesic. I'm controlling geodesics by geodesics. The control is given by a geodesic, the motion is given by a geodesic. Okay? So here is another one. The case of a Lie group. Assume Q is a Lie group. Why not? Let's see what happens. And L is arbitrary. I'm coming to the rigid body, just wait. Specialize this result if Q is a Lie group, H containing G, and the action is given by multiplication, right? Let's make it as simple as possible. And of course this is permitted. I take U in the Lie algebra. I look at the infinitesimal generator. I know what this is. If it takes on the left, the infinitesimal generator is given by a right translation. Okay. What is the problem? The Clebsch optimal control problem. In this case, I give you 2 points in the big group. I want to find a U of t in the little Lie algebra, a Q of t in the big Lie algebra, such that I minimize the total cost, subject to, here is literally multiplication, and I want to go from Q0 to Qt. Right? A very simple problem. Okay, I can write the variation principles down, here they are, I can write it here, right? And I know, I'm quoting theorems now. I know that my optimal control is given by this. I know this is automatically satisfied if I do what I'm supposed to do. Right? My Hamilton's equations, look, they become trivial. Alpha dot is equal to U times alpha. This is the action of the Lie algebra on T star Q. And the solution is given by alpha t gt alpha 0 for the base curve, Q of t is equal to G of t Q of 0, respectively this. I'm done. What does the previous theorem state in this case? For left action, or by G, the orbits are OQ, right? Just orbits multiplied in a group. Since the action is free, the normal metric here is given in this fashion. There is no perpendicular part, right? It's free. There is no isotropy. It has to be 0 at any single point, because the action is free, right? So, by the theorem, if the Lagrangian L is the kinetic energy of gamma, then the base curves, Q of t, are given in this fashion, G of t times Q0. They are, in fact, geodesics on the orbit with respect to the normal metric on that orbit. And this is completely coherent with Euler-Poincare interpretation, saying that G of t is a geodesic with respect to the G invariant divided by gamma. In fact, I knew this result by Euler-Poincare theory. And yes, it's true. And I do the inverse representation, forget that. Okay, n-dimensional rigid body. Let's apply this theorem to G equal to S1 and H equal to Gi. Why not? Right? This is going to give us what is called the symmetric representation of the rigid body. I'm sure you have not seen that. Okay, I can also consider this if I want to. It doesn't matter. In fact, it's remarkably simple. Well, I look at T of S1, which is in Tg around. Right? But this I can trivialize. Lie group times Lie algebra. So I can think of any element as a Q and a V, where Q is an SON guy and V is in GLM, general M matrix. Well, let me denote V equal to Q times U, where U is in SON. Okay. I identify the tangent and the cotangent bundle with the usual thing, trace of the transpose, the product of the transpose. Okay. This, in fact, is a bi-invariant Riemannian metric on SON. It's in fact the minus the killing on SON. What is the optimal control problem in this case? I give you 2 points in GLN. I'm supposed to find U of t, a curve in SON, skew-symmetric matrices, and the curve in GLN, such that I minimize this, subject to the following condition, Q dot is equal to QU. I go from here and I end up here. I copied line by line what I did before, abstractly. Okay, and this corresponds to the right action of SON on GLN, even though the rigid body is left invariant. This is the nightmare between the right and left. You have to be very, 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 very careful. Okay, so now you want to see what is the, there was a momentum map, remember, to compute this. The cotangent bundle momentum map J goes from here to here. So who is this? You sit down and compute it. It's an exercise. Q transpose P minus P transpose Q. Okay, let's apply the theorem. The theorem says that the optimal control U is found by solving the equation del L del U is equal to this, which we know is automatically satisfied if I solve the Euler-Poincare equations. Okay, fine. If QMP sit here, then J of QMP, which is equal to this, in fact is Q minus 1P. This recovers the usual momentum map associated to reduction on the left. Right? You bring it back to the identity. That's what it is. The Lagrangian of the n-dimensional rigid body is 1/2 Ju. Okay? So, what are the problems? How do you write this problem down? The L del U is equal 1/2 Ju, and the optimal control is given by J minus 1 of this. So, what are the Pontryagin Hamilton equations going with this? Well, I know what they are. I use this formula for the cotangent drift of right translations, and I write Hamilton's equation of T star GI. Here they are. Q dot equal to QU, P dot equal to PU. What does the theorem say? That if you have a solution of this, and if you set M, here it's U, equal to that, that satisfies Manakov's equations. It's quite amazing, isn't it? Q dot equal to Q, P dot equal to PU, U is equal to this. If you want to compute U dot, you get Manakov's equations. U dot equal to U and the omega that goes with it. This is what is true. And of course, I mean what I say, because look at the Hamiltonian. This is the M and this is the J minus 1. This is M omega. Literally. So, our motivation, one of our motivations was to understand these equations. I mean, I didn't know what the hell they were. You can do this computation. It's magic. I'm saying, take these equations, then form M to be this, and you will find each one. Just like this. Of course, in this audience, what are the other ones? For the other semi-simple algebra from Enko? I don't know. But it's an exercise. It should be possible to write. Okay? Why did I call it Krebs optimal control? Because it is Krebs. It is the Krebs variables in fluids. Let me show you it. So my Lie group, quote unquote, is the diffeomorphic group of a given domain. Compact Riemannian manifold. Now I form the group of the one that I really want, volume preserving diffeomorphists. Remember, I had a big group and a little group before, right? Here are my big group and my little group, my H and my G. I want to apply the theorem, that corollary, over and over and over again. Exactly as I did with GLN and so on. Okay? Okay, so, recall that the curve here represents the Lagrangian motion of an ideal fluid in domain D, etc., 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 like Arnold has done. And you have a Lie algebra, which is which I call X vol or X div. These are the divergence of vector fields tangent to the boundary, and the relationship between U and eta is the formula of the Eulerian velocity, which is given here at any frozen time. These are not derivatives. Any frozen time, you have this composition. Okay, this is called to the back to labels lamp in the literature. Okay, so here is Arnold, and even Marsden if you put HS. So, therefore, the Euler-Poincaré, the Euler equations are nothing else but the Euler-Poincaré equation on the divergence vector field associated with the Lagrangian given by the kinetic energy. Nothing new. Let's use the theorem in one approach. The first general theorem, left version, I am going to obtain a certain optimal control problem. Let's see what it is. I give you, what is the problem? I have to give you two diffeomorphists, eta 0, these are the Q's now. Eta 0 and eta t. We consider the optimal control problem, minimize the cost over all the vector fields, subject to the following conditions. Dynamics has to be given by the group action, and I want to get from eta 0 to eta t. Okay, so I have my L2 pairing. I have to compute momentum maps. I'm not going to go into details. Here is the formula for the momentum map on the cotangent bundle of T star of diff, with values in the dual of the volume preserving diffeomorphism groups. is just j of eta and pi. Of course, there's no separate. It's eta, pi is pi to eta. It's a covector. It's the Hodge projector of this object. So the Hodge projector of this object means it's this object itself minus the gradient of a well-chosen function, which you find by solving a Neumann problem. Okay. So, to make a long story short, what is the optimal control? The optimal control is what's given by. This is given by u pi composed with theta minus 1 minus grad k. Hamilton's equations are given in this fashion. This dagger means transpose relative to the Riemannian metric. This is not a dual. This is right. The variational principle is given here. Hamilton's variational principle. And we know, by general theory, that you must verify the Euler-Poincare equation, producing here the ideal fluid motion. Okay. Exactly as in the rigid body motion, Hamilton's equations are equivalent to the geodesic spray of the normal metric, of the tangent bundle, etc., etc., etc. Right? No, very, very clear. Let's apply the other theorem, the one that I didn't put with minuses. So this is the right version. Okay. So again, I give you two diffeomorphisms. I want to minimize this, subject to the law is given by taking the derivative of the multiplication, which now looks quite complicated now. It's a transport equation. I have to get from L0 to LT. Right? So the momentum map is going from here to the dual of the volume preserved diffeomorphisms. Now it's going to be more complicated. It's going to be TL with the transpose relative to the metric. I have to subtract from it a correct function obtained by solving a Neumann problem dictated by the Hodge decomposition, right? And my Hamilton's equations are given here, and I have a variational principle given here. By general theory, I know that U must satisfy the Euler equivalent. Okay. Let's compare. The n-dimensional rigid body was how? Q dot equal to QU, P dot equal to PU, JU is equal to this. Ideal incompressible Euler flow, look, it's exactly the same thing. L dot equal to this, pi dot equal to this, and U equal to this. There's the projector here. See? So now, of course, I can replace, I can do various other things. I can replace, but I'm not going to go into this. Average hydrodynamics, okay. I did this with you. Well, the same thing holds. I can do optimal control for Encke-Massa-Holm equation, dimensional Encke-Massa-Holm equation is the same thing. There the metric is going to be the Sobolev H1 metric. Let me see if I have this written down somewhere. No, I shouldn't go. It is one example after the other. I give them to you. It's one example after the other. There are double bracket equations, double bracket equations, etc. Let me stop here. Let me stop here. They're just examples. So now you have seen basically all the subjects in the MegaGrant. This is going to go on the web. What you have not seen yet, and we'll do this next time when I come back, I want to show you something about the numerics. I'm not a numerician, so I can't show you nice movies, I can't show you nice pictures, but I can show you what you are supposed to do in geometric integration theory. And it's very interesting. Very interesting. As geometers, we have work to do. In other words, let me tell you what the subject is. Take Kobayashi no Mizu, two volumes, and replace everywhere the manifold by a set of points. Okay? Rewrite the book. That's the goal. Literally. This is what these people want. This is called discrete differential geometry. It's a contradiction in terms. This can be differential the other way around, right? But this is what they call it. This is what is called discrete differential geometry. What is a vector field? What is the tangent bundle? Tangent bundle is Q cross Q. Well, it's not anymore a vector space. So what do you do?
Some algebraic geometry.
Some algebraic geometry may come in also. Right? You want to discretize the diffeomorphism, right? I mean, keep going and going, right? What is a discrete connection? What is a discrete curvature? What is a discrete method? There are many open questions which appear in applications. This is not abstract nonsense. They really appear in applications. They appear in mechanics when you want to do reduction. So I'm going to show you something like this. And here very little is known. It's all done by at this point people try to do things. Engineers are involved in this, a lot of engineers. Computer graphic people start reading Cartan and so on. I'm not joking, it's quite astounding. I don't know what I understand.
Elie Cartan or Elie Cartan?
Elie Cartan. This is hard for us. They are reading Elie Cartan. Computer graphics people. I can give you names. I was stunned when I saw it on their desk. Elie Cartan is very hard to read. So you see what I mean? It's a real problem. I mean, but this is the next time. This is sort of the last one of the major subjects. And any other subject that is connected with it in some sense is good for the So this is very vague, very broad, essentially anything that is remotely connected with this is good. Okay? Thanks. So next time I'll show you more about the last subject.